I knew it was slow. I was just like, oh, mad. That next one is not that. 6 times. It's definitely like not even, it's not even like it's really like I'm running like for like 10 seconds.
Okay, let's go ahead and start. So today we're going to talk about a part of the whole compilation process that's sort of the part that doesn't get any respect and nobody ever talks about, but it's called linking, which is the concern of when you've compiled your code, typically as a set of multiple files, how does it all get pulled together along with the various library code to form an executable program? And like I said, it's an area that is sort of an offbeat area. I think that the chapter in the book we have is probably about the most extensive coverage you'll ever see of linking. But it's an area where if you don't understand it, you can really get yourself into trouble. I'll show some examples of that. And if you really understand it, you can become a sort of power user and do some pretty cool things. So we'll cover that as well. So imagine we have a program that's sitting in 2 different files, main.c and sum.c. And main, of course, is the main function, but it calls a function called sum. And sum is declared in main.c, but not defined. And then there's a separate file called sum.c, where the file, this particular function is defined. So that's one important distinction. Declaration means there's some statement about, in the case of a function, what return type it has, what argument types it has. But a definition is where you actually provide the code for the function. So the job of a linker then is to, well, the normal compiler would take those 2 files and create .o files. But those are sort of only partially parts of executable code, the .o files. They're like the representation of the individual files on their own. And it's the job of the linker to then pull those 2 together and also some information about the libraries to create an executable program, which we'll call prog here. And so that's sort of the fundamental job of the linker then, is somehow to resolve these different pieces, that there's a function declared in one file and used in another. So how does then the final code get pulled together and know how that original function is supposed to call this external function? So why are there linkers at all? Well, partly this idea of separate compilation. You want to be able to compile individual files. And you can imagine for the kind of scale projects we do in this class, it's not so important. But when you have an entire operating system or the code base of a major corporation, there's a huge amount of code that all has to get pulled together to form things. You don't want to have to run the compiler over and over again every time you change one line of code somewhere. So this idea of separate compilation is important. And the other idea is this idea of libraries, that we make use of printf and a2i and scanf and malloc and free, all these functions we call routinely, and somehow those have to get, the code for those has to be brought in so that our program can access them as well. And then there's, so part of it is just the convenience factor. The other is efficiency, that we want to be able to have this executable program when it's all set up to run without a lot of overhead, making calls to maybe external functions. And also we don't want to have to replicate copies of, say, the entire C library over and over again in every executable program we make. And so that's an idea we'll call dynamic linking, and that's a big part of what we'll talk about. So the key part of it then is this resolution, this sort of key activity is what they call resolving symbols. So a symbol is the name of a variable or a function, and somehow we have to, we might reference it in one place, we might declare it in others, we might define it in some, and where does that all get put together? So we can see this sort of with our real simple example is actually a pretty good starting point. As I mentioned, there's actually in this code, there's 3 different symbols. There's within main, there's this global variable called array, and then there's the main function, and then in the function sum, there's a function called sum. And so those are the 3 symbols in this program. One thing you'll notice is that argc, argv, val, those aren't symbols because they're just locally declared or locally used variables. And so the linker doesn't know anything about them. Only these things that somehow have a global extent or involve global declarations exist in a way that the linker even knows about. So let's actually just look at some examples. And our friend object dump, when you give it the flag -t, can tell you about the symbol table in functions. And of course, like a lot of things, it looks very cryptic until you get used to what it's saying. But you'll see down below the 3 symbols in the that are somehow appear in the function main. The first is the main function itself, and it's declared as part of the text. Remember, text is the sort of misnamed where the code is. It's not text like strings. And there's this array that's also declared there. And then you'll see sum is listed, but it has this parameter star UND star, meaning it's not defined in this particular function, but it's somehow referenced, so it's something that the linker is going to have to help resolve. If we look at the code for main with object dump, if you say, show me relocation information and code, so you remember looking at disassembled code, you'll see that there's, we'll look at this on a slide, but the first, there's some funny entries there. You see the R_, x86, 64, 32, and PC 32. That's information, basically what's happened with object dump is it's merged information from the symbol table into the disassembled code. That's what this argument I gave it, you saw it was -rd. So disassemble and show relocation information. And what that's saying is that this particular line, the first one is going to be where the address of array, this global variable, will be put, somehow inserted into the code. And then the second is where the call to sum is going to be, and somehow that's going to be put into the code. So the point being that this original .o file, although it contains this in binary form executable code, it's incomplete. There's some words in there that aren't fully filled in, and it's the job of the linker to actually insert into those bytes in the code the exact address information that's going to be used in the executable program. So we'll see how that takes place here. One of the kind of interesting lessons about this too is how the linker is really, it's not a compiler. It's sort of a past, it assumes that the code has already been compiled and there's just enough information in the symbol table for it to be able to do its job, which is simply to overwrite a few bytes here and there of code, so the final, and then pull it all together in one big file, so that you have an executable program. So the job of the linker then is to merge these separate code files and the data sections of the program. You remember data is where the globally declared variables are, into common areas in the final file. And then to deal with these symbols that need to be resolved and make it all so that the final file is the executable code that you want. So as I mentioned, there's the .o file is sort of the start of an executable program, but not a complete program. It's called a relocatable object file. And it just has the code that the compiler has generated that describes everything except the global variables are kind of in this odd state, a partially unresolved state. Then the final file that becomes the executable is called an a.out file. In ancient times, I guess maybe it's still true, if you don't give a -o designation to GCC, it will produce a file called a.out. And then there's another kind of file that we'll look at called an SO file, which is used for shared libraries, and we'll come to that. So a shared library is a little like a .o file, except it contains information that allows the linking to be done right at the last minute of the program. If you're familiar, if you ever were a Windows user and you're always struggling with DLLs, dynamically linked libraries, that's what a .so file is. And so all these are represented in a common format called ELF, which is a standard that actually isn't just for x86, it's across any sort of Linux style of machine, all have this common format called ELF. And so you'll see that term, ELF binaries. And an ELF file then contains a lot of little pieces to it. And when we use object dump, what we're doing is we're sort of examining bits and pieces of that file. So if we say -d, it says we want to look at the text section and disassemble it for us. If we use the -t flag, we're saying, just tell me give me the symbol table out of this ELF file. Some other ones that are useful to know about there's sort of general information in the header, like what class of machine it is, what's the Indianness of this program, and so forth. The .text section is the executable code. The RO data is for data that's read-only but globally declared, and that will typically include things like string constants. Your printf format strings will end up in this .ro data. Then there's .data, which are the global variables that have been initialized. And then another region called BSS, which has various interpretations, but I like the term better save space. The idea of a .data section is it's an array that you've given some non-zero value to potentially. And so all that information has to be stored in the executable program to be able to read it in, some tables and things. But if you just declare an array, it just gets thrown into BSS if you don't initialize it. And what happens is when that all gets pulled together, it gets zeroed out. So it saves a little space in the executable because it's just going to set it to 0, so it doesn't have to store the actual 0 values in the executable. And then there's various sections that are shown in gray, which are more used for resolving some of this information. I'll also mention it, we won't really go into it, but the .debug section is interesting. That's how GDB works. So, or any other debugger, you've noticed you can, when you have a source code available, you can set breakpoints and examine variables based on their names in the program. And you might think that somehow this GDB actually has access to your source code, and it's figuring all this out. It's actually the secret is all contained in this .debug section, which we're not going to really talk about. But it contains basically the line numbers of all the program points and the names of all the variables and how those map to parts of the executable file, so that you can, it looks like it sort of knows what it's doing, but it really doesn't. GDB doesn't really know much, except it can have a pointer from in this table to say, if the user says, set a break at line number 171, well, 171 corresponds to this address in the code, so set a breakpoint at that address. And so that's described here. So the .rel information is this relocation information. That's how to relocate both the text or the code and the data, the global variables. And so I showed you that a version of running object dump. What it's doing is it's taking the rel.text section and mapping that and showing how those fit into the different parts of the code. Okay, so there's a few kind of general principles we have to understand here first. One is this idea of symbols. So I said a symbol is either a variable or a function, and somehow that kind of escapes out of this particular file and is known to the linker. And so in general, those will be ones that are defined in one part of the code and referenced or potentially referenced in another. And so within a file, then there's some external symbols, ones that the definitions exist elsewhere, and some local symbols, ones that are defined in this particular file. And so symbol resolution is basically figuring out what symbol means what file actually contains the real definition of this particular symbol, and that the linker should then reference from all other files. And it's pretty simple in this case. For example, array is a symbol that's defined and referenced in the same file. Main is defined in the main function, and then that's of course used by the compiler to set up the beginning of the program. A sum is a case where it's defined in one file and referenced in another. And as I mentioned, things like val and argc and argv don't show up in any symbol tables because they're not known, they don't exist. The linker doesn't have to keep track of them. And similarly, these other variables within sum. So here's a little test of your thinking. Here's a bunch of names on the right. And the question is, which of those actually become symbols in this file called symbols.c? So let's just do the answers are either yes or no. So let's just do a little. What about time? Yes, time is a global variable. Food? Yes. A? B? Right. So those are all local variables. Same with argv, argc. What about main? Printf? Anything else here that looks like a symbol to you? This is a trick question. So actually this format string shows up in the symbol table because it goes into read-only data. So you can look, we can we can get our answer then with tools. We can see at the bottom, foo, main, printf, and time are all symbols. And then there's something called rodata.stir1.1, and you can't see the value of it, but that's actually that format string. So that's kind of an obscure point, but the point is that constant strings like this are sort of treated a little like global variables, but they're put into read-only data so that if you tried to modify that string, you'd get an error. Yes?
And that's every time you use a string like that without like assigning it to a variable or something.
Well, even if you assign it to a variable. So if you said something like char star f equals, quote, howdy, unquote, that string howdy would be allocated and stored in rodata. And then your variable would be given a name. And now if you said, if that name is, actually that's a good question. We'd have to try that. That's an so you said char star s is equal to some string, and then you edit it. I don't think it'll like that. It will not be happy. Yeah, you can try it. Now if you said char star buff of 10 is equal to a quoted string, then you can modify the elements of buff. Because what you're doing is creating an array and initializing it. But if you give it a string constant, that's just what it says, it's a constant. So you can change s to point to a different string, but you couldn't change the contents of that string. I'm pretty sure that you could double check by trying to compile it, but I'm pretty sure that would happen. It's a good question. Okay, now there's an interesting sort of nuance here, which is the things that are declared as static in a file. So you know that static has, like a lot of things in C, has multiple meanings depending on context. So one of them is if you want a sort of semi-global variable, a variable that's accessible within this particular file, but not by the rest of the program, then you should declare it static. And static is actually a very good habit to get into, including making your functions static if they're not going to be referenced elsewhere, just to avoid sort of name confusion, especially if you use names like X. So anyways, you know that to say something is static in a file makes it sort of a variable that's global within this file, but not accessible outside. And then there's another version of static, which is if you declare a variable within a function, a local variable within a function to be static, then it's essentially shared across all calls to this function. So for example, you see 3 different x's here. Those are actually, will all be 3 different variables. The main one called x is accessible, for example, by this function h. The function, the one within f is only accessible by calls to f, and the one in g is only called by calls to g. And the other trick is that where it's given a value like 17 or 19, but that's only done the first time the function is invoked, or maybe the first time it's invoked, and thereafter it won't change. So it's a way you can, it's just a tricky way you can sort of hide information in a program. So it turns out that all 3 of these will end up being symbols, even though they're local to this, and that the linker is going to have to help resolve them. And then you say, yeah, but how does the linker keep track of 3 different x's all in the same file? Well, what it does, if we look, let's see, I've got a bunch of examples here. you'll see up sort of midway through, see if my pointer's working, that there's 3 x's, but one of them is the sort of global variable x that's for the whole file, and then this x.1721 and x.1724 are the sort of hidden versions that are within this particular set of functions. And so if I look at the, yeah, it's kind of messy to figure it out. But you'll see that somehow all 3 of these functions need to have some relocation information provided to it, without going into the details there. So the point is, even if you declare a variable, if you declare a variable as static, let me also see. If we can figure out, yeah, it's not totally clear from here that like the variable x is only accessible within this particular file. But I think somehow that's built into the symbol table. I don't remember all the exact meanings of those various D's and capital O's and things. Yes?
Does the x inside f and g like shadow the x that's accessible to all 3 functions?
Yes. So if you were to run this, which I don't think I have set up to do, this x is shadowing this variable x. So I'd be, these functions all refer to the 3 different x's.
And so you have to give it a different name with more x's going?
Yes, right. Yes.
Why do the static variables go in the symbol table if they're only just the accessible file?
Because it's still the job of the linker to merge the, remember in these .o files, it has each of these sections, the different data sections and the text sections are all in there. And then in the final ELF file, it needs each of those sections, but it has to sort of pull them out and concatenate them together from the different files. So it needs that information to kind of build up the executable, even if it's not trying to resolve the symbols across the different files. Make sense? These are good questions, buddy. So this just says what I said. Allocate space. Actually, it allocated them in BSS. No, it should have allocated them in data. And then but it gave unique names to the different ones. So when there's multiple symbols declared in multiple files, how is the linker supposed to know which one to use? Where is it actually defined? Which definition should it use? And so there is sort of a kludgy way that it happens by default. And I'll talk about the way you can make sure it really happens the way you want it. But let's talk about the kludgy way first. And that is every symbol is either classified as strong or weak. And a strong symbol is one where there's an assignment made to a variable, or there's a definition of a function. And a weak symbol is one where it's just referenced or it's declared, but it's not actually given any definition. So for example, in this case, you see that foo is strong in P1 and weak in P2. And the functions P1 is strong in P1 and P2 is strong in P2 and not weak in either place, not used in the other places. And so the general rule is if you have multiple strong symbols, then you'll get a linker error. It'll say multiple declarations, blah, 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 and it won't link your code. The other is if there's a strong in one place and a weak in another, then the strong beats the weak, as you can imagine from the name. And if there's multiple weak symbols, and this is the kludgy part, it'll just pick one and say, oh, okay, that looks good. We'll use that one, which can get you into trouble. So let's look at some problematic aspects of these rules. Actually, let's do some puzzles first. So imagine running these. Each of these pairs will be, imagine code sitting in two different files. We try to compile and link it. What's going to happen? So here, what will happen with the first one if we try to compile it? So is P1, is it strong or weak in the two files? It's strong in both, right? So that'll give an error. The linker will say, can't do it. What about the second one? So now I'm calling P1 and P2, so they're distinct. And X is weak in both places, and so it will just say, okay, I guess X is, it will basically arbitrarily choose which of the X's to call the sort of the globally used X. Now we get into some funky stuff. So what if we have, you'll see X here on the next one is weak and in both places, but it's declared with two different types. What do you suppose will happen there? This is where it gets kludgy. Yeah, I think, you have your hand up? Yeah.
One code file will always like interpret it as a double, and the other will interpret it.
Yes, potentially. Actually, if you run this code, you'll get a warning to say two different sizes, because the double is 8 bytes in one and 4 in the other. But it will actually link the code for you, and when you run it, probably what will happen is when you change X in the right-hand file, it'll zap the values of both X and Y in the left-hand file. Probably. You know, all these are sort of depend on random things happening. But the point is it will do it. And actually, I'm going to run through this example and I'll show you some code where it really does do some fishy stuff. And then this is a case where it's a similar problem, except instead of just sort of randomly choosing it, it's strong on the left and weak on the right. But the point is the linker does not do type checking. The linker actually, it knows how big something is, but it doesn't know its data type. So as I mentioned, I think what you'll get on these is a warning message, but not an error message that says you're trying to link things and these variables have different sizes. And then the final case is this sort of the good thing. So this sounds really bad, and you could see a lot of bad things happening. And in fact, here's a real example where I declared a long int, so it's an 8-byte integer, and a double, and you'll see that the linker is perfectly happy linking these two files with no error messages at all. And so let's see what happens. So I type mismatch, and it's supposed to print the value of X, and it prints some long big number, right? So anyone figure out why it printed that number? Yeah.
So you're storing this double 3.14 in the memory that X is pointing at.
Yeah.
Main is going to see that's int, and so it's a 20 like int
Yeah.
value which binary represents.
You got it. Exactly. So there's some bit pattern to 3.14, which is, as you know, there's all those bits up at the front with the, and so it ends up being a lot of bits, a lot of ones in there. And now the main thinks it's a long int, and so it just prints it as that. The point was that the compiler didn't complain, the linker didn't complain, everybody was happy except for me, because I had this really botched up execution. And you could imagine that happening, imagine that you're working at major global tech company, and this happens, and somebody's going to come around and point a gun at these two people saying, why did you commit that file? So, so something should be done, right? So how can we? Well, actually, it turns out there's a couple of things that are pretty important. One is to, if something really is not going to be shared across files, you should declare it as static. Just kind of keep it within the fold. And if it's going to be a global thing that you need, then you should use this extern declaration. And extern is sort of like a weak symbol, except it's even weaker, meaning that if the linker, you saw with these weak symbols, that in the end it will choose one and use that if there's no strong declaration. An extern, if there's no strong symbol with that name somewhere, then the linker is going to complain. It says, you told me there'd be something called X, but I don't know what X is. Yeah.
So you're saying that X would be defined somewhere else?
Yes. So extern is external. And the interesting thing, let's see, here's an example demonstrating this idea. And this is sort of one of the ideas of making use of a .h file. And you see in my .h file, I declare G to be an extern int. And I pound include it in two different files. So in the upper file, you see that it's truly is external, that int G does not, it's just referenced here, but there's no definition of it. You'll see in c2.c, it's actually defined in here. But the compiler is happy with that. I was just reading to make sure I believe this. You can say in this, because remember, pound include is not something magic. It's literally a direct expansion of that text within your file. It's done as a pre-processing step before the compiler really touches your code. So it's as if you just copied those two lines directly into this file. And so effectively, within a single file, I'm saying there's an extern int called G, and there's an int called G. But it's fine. That's sort of that's purposely allowed so that you can do these pound includes. And so the G will be resolved then to be this unique integer G that's defined in this particular file. And the good news about that, you see, is if I do it this way now, I won't have that mismatch of types. If everyone's using the right .h file, if it was used as a double in one place and as an int in another, then you'd have a complaint by the compiler, because it would say, look, you said the G is an extern int, and now you're trying to create a double called X, and you can't do that. Does that make sense to people? So that's sort of part of the purpose of .h files and the idea of externs. Question?
Yeah. So in the global.h file, even if you don't put an extern in front of the G, wouldn't that still make it a weak symbol?
Yes. So you could do the same idea of just take out that extern in global.h, and that would become a weak symbol. And it would, in this case, give you the exact same effect. The difference is if I omit that line int g equals 0, and I still have that extern, it will give me a linker error. It will say, you've told me there'd be something called g, but nobody's defined it. So with that extern, I have to, in one of the files, actually declare it. So it's the same idea, but it's a little bit cleaner to say extern. And this is another example that a previous lecture had put together, so I thought I'd show it. Is another style of .h files is to sort of, in a single file, kind of have different sections based on whether it's and local, the one that's actually defining this, whatever the file is, this variable, and the other that is just consuming that information. And that would be especially if you have a file .h that's the name of some, where you're declaring whatever data structure and API that you're going to give to some module. Then you might want different sections on whether this is the pound include within this particular file or not. So the example here is, if I say pound ifdef, it means if there's a compile time constant called initialize that's been defined, then use the red code, and if not, then use this black code. So now if I pound include global.h after I've defined initialize, and the default value initializes, it defines it to be 1, but the point is it's defined. Then here, this init and this g would refer to the red code, and up here where I don't define initialize, it would refer to this black code. And so this example is a little too small to appreciate it, but you'll see that's a fairly common pattern of, like if you go back to the C programming lab, you'll see that I did some tricks to use different versions of the of different functions depending on whether it was internal or external, whether it was your code or my code, basically. I'll show you that in a minute. Okay, so as I mentioned earlier in response to one of the questions is, each of these .o files has its own little, it's a complete ELF file, so it has all these various sections. And the job of the linker then is to pull those together and create the relevant sections in the final executable code. And this is something I already showed you. When I used object dump -rd, so where you disassemble with relocation information. And you saw this function called main that it needs to know where sum is stored. And so that's what this first relocation information is about. And then also where array is stored, and then it has to be able to call the function sum. And so it has relocation information there too. And actually, if you look carefully, you'll see that the initial pattern here is just all zeros for both where this array is stored and what function it's calling. And you can think of that as a placeholder in the code, 4 0 bytes that will get filled in by the linker with the exact bytes to use. And so when you finally compile this and link it together into a executable program, you'll see that in the end, this call has been filled in with the value 5. And this idea is it's so-called PC relative. So it actually, the true address of sum is given by adding 5 to this address, the return address. And you see that gives you this 4E8 address. And then up here, it's the global variable called array has been stored in an address 6101018. And so that's been inserted into these bytes of this move instruction. Okay, so the linker actually then pulled the text together, but it also inserted the appropriate values in some of the bytes of this code to give it the right references. So when the program finally runs, then it just is calling the right functions and accessing the stuff. So the linker has done the real work of getting this program ready to run. And then when your program first starts up, when you invoke it, that's called loading. When it brings it into memory, and as we mentioned a previous lecture, that's all spread around this virtual address space of your program. Some of it's used for your stack, but the parts that the linker is set up are these various sections that are code, data, some of it read-only and some of it readable and writable. Okay, so pull out your laptops and let's give this quiz a try. Oops. Okay, let's go ahead and see how you did. I have to confess that I didn't get all the answers right when I did it the first time either, so. Why is this thing so nasty? Oh, come on. What's your general feeling about Canvas, by the way? Well, let's see. Let me just go through it with you. Okay, sorry, technical difficulties. Question 1, you have 2 source files, you want to share them. Which approach should you take? What did you think? That should be kind of what I just said, right? Extern, you got that? Yep. How many of the following, which of the, let's just turn this into a which. Which of the following will be in the symbol table? My global 2? Yes. My shared global? Yeah, it will be in the symbol table, just be marked as not defined here. And then foo, right? So the answer is 3. Okay, back to caches. If b equals 4, capital B is 4, that means 4 bytes per block, and it's a 64-byte cache, and it's direct mapped. How many sets? 16, right? It has nothing to do with the address size. That was misleading. It just says that, because it's a direct map, so the E is 1, so it means that each of these bytes is part of a different, each block is part of a different set. Okay, and then the last one is sort of actually, the official answer is it's undefined. What I believe would happen if you ran it is it would actually compile okay, and then the linker would give you a warning. Because and it's not because it knows the difference between a double and an int, it knows the difference between 8 bytes and 4. But yes, it's undefined, would be a good way of saying it. Okay, so I don't know who got what answer, but that's the answers. Okay, so now let's move on now. We sort of now have a sense of what this thing's supposed to do. And let's sort of, the basic idea of linking, we've only looked at how do we link our own files together. But the sort of, one of the really big roles of linking is how do we link in all the library stuff? So back in the battle days, basically this would all be brought into a single file. You just compile the whole thing every time. But nowadays, in another previous era, you do what was called static linking. So static linking is linking, except you bring in all the files into the final executable. And you can do that. You can actually force it to happen. So if the library files are in an archive format called .a, and you can call a program called R for archiver and create, excuse me, your own library code. Excuse me. So this imagines it if you were creating the file for the C library called libc. You can archive them all together and create a big .a file. And then when you go to compile, and so for example, if you look on a machine, you can use the archive program, which is a little like tar, except without the T, in terms of the arguments you give it. So if you archive, you can actually look at all the functions, you can list all the functions that are available in the C library, each of them like printf, they're each in separate files. But that file is 4.6 megabytes. And the libm, which is the math library, is 2 megabytes. So the point is those all exist, they're in the standard place on a Unix or Linux system is /user/lib. And the other thing, you know, when you, So I can actually simulate, I can do this myself by setting up, if I have some other library I want to use and statically link it, I can do that sort of the same way that the C library is. So I can create an archive file called libvector.a, and then within some file that can make use of these, just like you would use printf set. I can call a function called addvec, which I've defined in this .h file called vector.h. And then somewhere off I can have built up this whole library of functions and then ask the compiler to link those in. So, so what happens if you declare in GCC, if you say static, it will link, do all the linking statically. And it will actually create a file that's almost a megabyte just for this very simple program, because it has to have copies of all the functions, not all of libc, but all the functions that it uses, which are a lot of them that are sort of under the hood there. But the point is that I can have introduced my own library here. And there's a little bit of a convention. You'll see that when you give the -L flag and give a name, the default is that the actual archive file then is lib, L-I-B, then that name, .a. And so -L says include in the linking a file called libvector.a. And this -L dot is saying, the capital L is telling the linker what directories should it be looking in for .a files. The default is in user lib, but by saying dot, that means in this local directory. So it's saying also look for .a files in my local directory, which is where I happen to have this libvector.a file. So all that obscure notation is there to tell the linker where to pull this stuff together to create the final file. So this is actually a pretty useful thing to know if you ever have to maintain a large library, that you'll end up using these .a files quite a bit. But it's not very efficient for a really large library, as you've seen. The other problem with it is, anyways, there's a whole thing here about how does the linker find these files? How does it know which ones to pull together? And basically, it will scan through the command line in the order that it's listed, and it will have the pull in the files. And so if my library code calls printf and my main original code didn't, then at the end it will also pull in printf of the libc. So it has to be able to sort of pull in more and more pieces of code as it reads code and those reference other ones. And you can get into sort of quirky linker errors where the order in which you list your files will make it work or not work depending on the order in which things are defined, and it can get pretty tedious. But that's a little off topic for right now. There's a few problems then with these statically linked libraries. One is that it's just, you end up with bloated code. You end up with copies of the same code in a bunch of places. But a perhaps more serious one is, what happens if there's a bug in a library and somebody wants to fix it? If that library has been statically linked in a bunch of other places, then there's no way to track those down and update them. And so there's stories, and there's a link here to a blog post in Google where they discovered a weakness in one of the commonly used libraries, exploitable flaw. And the biggest problem they had was tracking down all the places where that library code had been linked in statically, and therefore, even if they fixed the bug in their version of the code, that fix wouldn't get propagated to all these copies. So there's sort of a couple of reasons then why you don't want to statically link. And so that brings in this idea of dynamic linking with shared libraries. And so, for example, and as I mentioned, those usually have the extension .so, and those will be dynamically linked. And there's actually two forms of dynamic linking. One is called load time, meaning when the program is first brought into memory, getting ready to execute, then it will go and pull all the library information in and add that to the pile. And that's the sort of default. That's what normally happens. But there's another more clever thing where you can do runtime linking, where you can basically wait until the program is started and then link in a library. And I'll show you some of that. So let's just look at my examples a little bit. So that program, let me see what it's called. Oh, the one that involves main and sum. This one, so main calls sum. That gets compiled, and the statically linked version of it is called prog2. C. And it's all statically linked. And if I were to object dump it, I don't know if you'll be able to see that here. It's going to be a mess. As you know from looking at bombs, I can't get the right parts of it. But the one that's more standard is called prog2l, was just generated by the sort of default commands. And if you run a program called LDD, you'll see that LDD tells it what information does the, prog2 is a different program. Prog2 is this one with the vector library, sorry. So prog2, let me just go back to what I said. It's the example I said where there's a vector library that we want to link in. So you'll see that prog2 requires the standard libc, but it's also looking for a file called libvector.so. And it actually tells where those are located as well. So that's an example then where I have set up my own version of a dynamically linked library. And that takes a little bit of weird stuff with GCC. So first of all, I need to create there's a mistake in this slide. Excuse me. A little fix on the fly. So, with this magic incantation creates this .so file, the dynamically linkable vector. And so you see when I compiled it, I had to give this flag -fpic. PIC stands for position independent code. And it's a particular way of compiling the code and its references in a way that makes it possible for the linker to be able to shift the position of that code around in the file without in a fairly straightforward way. So that's required for executable library code. It's not the default. And now when I want to create this .so file, I have to now say, give this flag -shared to tell it that what I really want to do is, and so even though it says it's to GCC, it's really to the linker itself. It says create a file so-and-so.so containing these .o files. And if you haven't compiled it with PIC, it'll complain. So that's all sort of, this picture sort of shows that whole thing all as one step. You could start with the .c files, tell it that you want position independent code and that it should be shared into a vector, and that will create, that'll do what those two steps I just showed were. It'll create this thing called live-vector.so. And then the linker will build this all together, but as I showed you before, once I load the program is when it actually brings that library in and assembles it together into the actual program that's running on your machine. So this is called load time, meaning that the actual library code gets added to your code at the time the program is first being started up. Now you can do even a more exotic thing, which is you can basically, within your own program, call the linker. And so that's called runtime linking. And I'm not sure why you'd want to do this, but you can. I mean, I can think of some scenarios where you want to do it, but it's a little bit obscure. But the basic point is there's a library program called dlopen that you see it opens a .so file and it does what's called lazy, meaning it just opens it, but it doesn't do anything until you tell it to do more. And then there's a function called dlsim, which means resolve a symbol. And you give the name of the function as a string, and basically it will resolve that symbol for you using the linker functionality to create now a pointer to something, which will be this function called advec. And now you'll see I can call advec just like before, but the point being that advec really had no meaning whatsoever until I made this call to dlsim. It was a null pointer before. So it will actually fire up the linker, pull in, resolve, do all the appropriate resolutions of the symbols and so forth, create a pointer that then you can use as a program. Yes?
Why is it the case that if you only need one or two functions from a big library that you can only that you have to load all of them rather than just loading those two functions?
Oh, it will only pull in. The linker will do the same thing that the .a files is. If you have a bunch of functions in different separate files, it'll only pull in the files that you're actually referencing.
No, but functions in the same file, you have to pull in all of them.
If you had a bunch of files in one file, bunch of functions in one file, it'll pull that whole file in. The linker is not that clever, right? The linker kind of knows about blocks of stuff, and it has various pointers to it, but it really doesn't have this granularity of individual functions. So the lesson on that is if you're creating a library and you're worried about that, you should use a bunch of files. Good question. So this is all the magic you need to make that run, which is quite a bit. And you have to include this library, the dynamic link library. You have to include it because that library now becomes this code that's used to do the actual linking. Okay, I want to just finish with one real quick thing that actually gets pretty useful, and what's called interpositioning, which is when you want to track the calls to some function. And the most straightforward version of that is like for profiling, or for example, you've seen in when you did the C programming lab, you thought you were calling malloc and free, but you weren't calling the library versions of that. You were calling versions that we had where we were being a little careful about making sure you didn't have any orphans left over. You freed everything, and you'd get error messages if you hadn't. And valgrind's a little bit similar, that you can run valgrind on a program, and somehow magically it's keeping track of all your calls to malloc and free and figuring out if you have any invalid references in there. So valgrind is also making use of this idea of interpositioning. So there's sort of, and this is covered in the book, so we're going to run out of time, but let me just show you three ways you can do interpositioning. The most straightforward is compile time, and it just makes use of macros. So imagine I have a library, let's sort of call it a little library, where I've declared my own versions of malloc and free. But I want the users of this library to think that they're actually calling regular malloc and free. Well, if I just provide a .h file that uses #define to sort of alias malloc, my malloc with malloc and my free with free, then in that user's code, they might not know that they're being tricked, right? And that's exactly what the C programming library does, and you'll see that later this term when you look at the malloc. You're going to write functions called malloc and free, but they aren't really malloc and free. They'll get their alias to some other name. And the advantage of that is now it only works if you have control at compile time, but now I can do things, my malloc and my free. The difference here is that they print information about what's being malloced and freed. There's another version which is called link time interpositioning. So this happens as the linker is doing its work. So it's still part of the compilation process, but it's after the .o file has been generated. And it's this really kludgy idea that they set up just for this purpose, is that they put these little prefixes on standard names. So there's one called real, and there's the other called wrap. And so the wrap is the one in your in the code that's being interposed on, and the other real is the one that calls the actual library routines. So for example, I can declare functions called wrap malloc and wrap free, and they call real malloc and real free, because real malloc and real free are the real thing, and the wraps are the phonies, but the linker will later substitute in the wrap names in there. And then if I pass a whole bunch of flags to GCC to do all this wrapping of malloc and free, you'll see that it actually will create this code that is making use of this new library, this interposed library. And the final version, I'll just describe it here. And like I said, it's worth reading this part of the book if this is interesting to you. Is this really clever one where you make use of this dynamic linking, and you basically, at runtime, as the program is basically being pulled into memory, it magically will interpose on the library. And just to demonstrate this possibility for you, let me show you something totally cool. Totally cool if you're a nerd. So the idea is there's this program called int_r interpose, and if you look at the code, it's just calling malloc for as many bytes as you're passing on the command line argument. And the normal version doesn't do anything interesting, but if I set an environment variable called load preload with the name of my library, my desk.so file, so my dynamically linkable malloc library, then I will, when I call this function, then int_r, this program, at the link, when it's being pulled together, it will actually use that library rather than the standard libc.a. And what's interesting about this is you can interpose anything as long as it was set up for dynamically linking. So even the ls command in Unix, you'll see, makes a bunch of calls to malloc and free. And you can see exactly what calls it's making there, even though I didn't recompile ls, I didn't relink ls. What I did is ls is a dynamically linked piece of code that usually sits in I'm not sure where it usually sits, but it's just a piece of code there that normally gets pulled in, dynamically linked with the regular C library and executed. But in this case, I sort of told it, oh, use my own custom library to do it. So you can imagine if you're trying to track down, you're given an executable program that you don't have access to, but you want to understand it better, you can use this interposing trick in some pretty clever ways. Okay, we'll take care of this.